Hello, young chemists. What is up? This is Mr. Rosen. Today we're going to talk about effusion and diffusion of gases. So, effusion of a gas is where you have a gas in a container, and let's say you poke a hole in it or open a little valve, and the gas escapes through the opening. Okay, so when you have a gas in a container, the gas particles are going to be bouncing around inside of that container. So like let's say that this is our container, right? The gas particles that are inside of it are going to be zooming along until they hit a wall, and then they will bounce off of the wall, right? This one will be moving along and then it'll bounce off of the wall. These are all just moving around and bouncing off of the walls, right? They're all in constant motion, bouncing around. But if you have a container and there is a small opening in the container, right? Here's a very small opening in the container. The gas particles will continue to, bounce off of walls. But every once in a while, a gas particle will be moving with just the right trajectory, so it would go to hit the wall, but the wall wouldn't actually be there, and it would pass through the opening and effuse, right? This is the idea of a gas leaving a container through a small opening. That's called effusion. There's also diffusion of gases. Sorry about the bell. The diffusion of gases, as it says down here, is describing the movement of one gas through another gas. So, we live and breathe our atmosphere, which is a mixture of gases. Anytime you smell something, it's a gas molecule moving through other gas molecules to reach your nose. So that's diffusion, a gas moving through another gas. Both effusion and diffusion follow Graham's law of effusion, which says that the rate of effusion or diffusion is proportional to 1 divided by the square root of the molar mass of the molecule. So thinking about what this means, if you have a large molar mass, you're going to find its square root, and it would be some number. 1 divided by a larger number would give you a smaller number. And if you had a small molar mass, right, its square root would be even smaller. So 1 divided by a small number would give you a large number. So thinking about how that, what that means or how that makes sense, that means that a small molar mass would have a high rate of effusion / diffusion. So if it's a lighter molecule, it will effuse or diffuse faster. If it's a heavier molecule, it will effuse or diffuse slower. And this makes sense if you think about it in terms of the formula for average kinetic energy, 1/2 times mv squared, where v is velocity and m is mass. So if the mass increases, the velocity decreases, meaning at the same temperature, a heavier molecule will be moving more slowly. A lighter molecule will be moving more quickly. So if it's diffusing, meaning moving through another gas, the lighter molecules are moving more quickly, so they'll diffuse faster, and that makes more sense. If they're heavier, they're moving more slowly, so they'll diffuse, meaning move through another gas or move through the room, let's say, more slowly. So let's do a couple of examples, example problems. So the first example problem here, it says, butyric acid smells sort of like rotten cheese. It's like putrid smelling, and has a molar mass of 88.11 grams per mole. Acetic acid is what gives vinegar its smell. Okay, and has a molar mass of 60.06 grams per mole. If a container of butyric acid and a container of acetic acid were opened at the same time on the other side of the room, which would you smell first? So which molecules would reach you first? So this is basically saying which of these two molecules will diffuse through the room faster. So if we want to compare them, the rate of butyric acid, I'll call butyric acid BA. So I'll write the rate of BA, butyric acid, is 1 over the square root of its molar mass, which is 88.11 grams per mole. And the rate of acetic acid, we'll call that AA, is 1 over the square root of its molar mass, which is 60.06 grams per mole. So the rate of BA equals, and so here in my calculator, 1 divided by the square root of 88.11. Okay, so 1 divided by the square root of 88.11, I get this number, 0.1065. Then if I want to do the rate of acetic acid, that's 1 divided by the square root of 60.06, and I get the rate of acetic acid is 0.129. So if we look at the rates, this is a smaller number than this. So that means that acetic acid has a higher rate of effusion or diffusion. And that makes sense because it's the lighter molecule, right? The lighter molecule will be moving more quickly, so it will effuse or diffuse faster. So the one that we're going to smell first is the acetic acid. It's the lighter molecule. It will effuse or diffuse more quickly. Okay, so we would smell the acetic acid scent first. Now, you could ask you a question that says something like B. It says, based on your answer above, how many times faster would the first scent you reach? How many times faster would the first scent reach the customers? Or this is sort of rewritten. Sorry, it's just supposed to say. You could just say reach your nostrils. I'm using a problem that I copy pasted from something and I changed it a little bit. So how many times faster would it get to you? You're really just comparing these two rates. So the rate that we're interested in is 0.129, right? If you take that and divide it by the rate of the other one, 0.1065, it's going to tell you how many times faster it is. And they're pretty similar, but about 1.21 times faster. So the acetic acid would reach you 1.21 times faster than the butyric acid, or the other way around, butyric acid would take 1.21 times longer to get to you, which the next question is kind of asking. It says, if it takes 72.3 seconds for the smell of acetic acid to reach you, how long would it take for butyric acid smell to arrive? And we just realized that butyric acid will take 1.21 approximately times longer to arrive because it's the heavier molecule, so it'll be moving more slowly. So all we have to do here is take 72.3 seconds times 1.21. So this number is still on my calculator, just say times 72.3, and it'll be about 87.6 seconds. So if it takes 72.3 seconds for the acetic acid to arrive, it's going to take about 87 seconds for the butyric acid to arrive. It'll take longer because it's heavier and is effusing or diffusing more slowly. All right? So let's do a couple more problems. Number 1 here says, what is the relative rate of diffusion of Kr compared to helium? Does Kr diffuse faster or slower? So the rate of Kr is 1 over the square root of its molar mass, and the rate of helium is 1 over the square root of its molar mass. All right. So for each of these, helium has a molar mass of 4 grams per mole, and Kr has a molar mass of 83.8 grams per mole. So I'm going to get the rate of each of them from the calculator here. I'm going to take 1 divided by the square root of 83.8, 0.109, and then 1 divided by the square root of 4 is 0.5. So the rate of He is much more than the rate of Kr. And that makes sense because He is much, much, much lighter than Kr, right? It's like a 20th of the mass of Kr. So this has a much higher rate. So what's the relative rate of diffusion of Kr compared to He? So if we're comparing them, Kr compared to He, it'd be 0.109 divided by 0.5. Okay, so 0.109 divided by 0.5 gives us 0.218. Okay, so this is the rate of Kr compared to He, right? It's at about 1/5 of the rate. Does Kr diffuse faster or slower than He? It diffuses much slower because it's heavier. Okay? If the He in problem A takes 20 seconds to effuse, how long will Kr take? So if we're interested in Kr, we can use this number as is, and we would divide by that number, or we could flip the rates around and we'd be multiplying by the number. So the helium takes 20 seconds, and we know that the Kr is going to take longer than the He. So we could take this and divide it by 0.218, and what we would get if we took 20 and divided by that number is 91.7 seconds. If that's a little bit confusing, the other thing is if we switch these around, okay, so like if we took 0.5 and divided it by 0.109, right? So on the calculator, we'll take 0.5 and divide it by 0.109. You would get 4.59 approximately. And what this is saying is that the helium would effuse or diffuse 4.59 times faster than the krypton. Or the other way around, the krypton would take 4.59 times longer than the helium. So if we took this number times 20, we would get, and you'll see, it's just going to be the same number, right? 91.7 seconds. So you can really do it from either way. It just depends on which rate you're dividing by the other. So as long as you understand which will be faster and which will be slower, you can come to the right answer. So question number 2 says, if it takes 16.2 seconds for a sample of neon gas to effuse from a container at a certain temperature, how long will it take for an equivalent amount of xenon gas to effuse? So we have to kind of do the same stuff as above here, okay? Rate of neon is 1 over the square root of neon, which is 20.18, and the rate of xenon is 1 over the square root of xenon, which is 131.29. Okay, so let's just see what we get for each of those rates. So we're comparing them. 1 divided by the square root of 20.18, 0.223, and 1 divided by the square root of 131.29, we get 0.0873. Okay, so the rate of neon is larger than the rate of xenon, which you'd expect because it's lighter. And it says that the neon takes 16.2 seconds. So if we take the rate of neon and divide it by the rate of xenon, okay, so 0.223 divided by that's 0.0873, that's going to tell us how many times faster the neon diffuses or effuses. So 0.223 divided by the rate of neon, or sorry, the rate of xenon, we get 2.56 approximately times faster. So what that means is the neon diffuses about 2.5 times faster than the xenon does. So if it diffuses that much faster, that means the xenon's going to take 2.5 times as long to diffuse. So we can take 16.2 seconds and multiply it by that rate difference, which is 2.56 times. And that will give us how long it will take for the xenon to diffuse, which is about 41.4 seconds. So you can see that the xenon has a larger molar mass, so it has a lower rate of diffusion. It takes about 2.5 times as long, and if the neon takes 16 seconds, the xenon's going to take 41 approximately seconds. Our final problem is a little bit different. It's actually having you solve for a molar mass. So it says an unknown gas diffuses at a rate that's half of carbon dioxide. Calculate the molar mass of the unknown gas. So if you look at what we have here, it tells us that we have carbon dioxide. So we need to calculate the rate of the carbon dioxide, which is 1 over the square root of its molar mass, which is 44.01 grams per mole. If we do that and we look at the rate, we can actually take that rate and then divide it by 2. So 1 over the square root of its molar mass, we get 0.151 approximately. Okay, so that's the rate of CO2. Now the question says that the unknown gas diffuses at a rate that is exactly half of that. So if we take this number and we divide it by 2, we'll get the rate of the unknown gas. Right? So I'm just going to take this divided by 2, and we get about 0.0754 approximately. So that's the rate of the unknown. Now, we're going to take this rate and plug it into an equation just like this because we know the rate. So it's 0.0754, and rate equals 1 over the square root of the molar mass. We're solving for molar mass, so that's our x. That's what we're solving for. So this is what we have to figure out. This is what we have to solve. Okay, and you can set this up as just sort of an equivalent statement here, an equality where this over 1 equals 1 over this. So if you're solving for x, you would cross multiply and then divide. So basically, if you take 1 divided by 0.075, you get this number, 13.26. Now, 13.26 is equal to the square root of x. We need to solve for x, so we're going to square on both sides. And if we take this number squared, I'll just draw a little arrow over here. So we're going to square that number. We get x equals 176.04 grams per mole. That is our approximate molar mass. And if you want to, you could always plug it back into this equation. You could say 1 divided by the square root of this, and you'll see that the rate is, in fact, this number, which is half of the rate of CO2. So this is just another variety of a effusion-diffusion problem. There are multiple varieties. Hopefully this has been helpful. This is effusion, diffusion. Keep working, keep practicing. Good job.